start. My name is Pavel. I work at Align Technology and R&D, and I want to talk to you about asynchronous programming in C++ today. What we're going to cover are std async, std future, promise, and package task facilities. Who is not familiar with these facilities? Raise your hand. Okay. As an illustration, we are going to look at what offers PPL, Parallel Patterns Library from Microsoft. We are going to look at concurrency task and continuation and cancellation and task composition. What we are looking for also is coroutines. We'll try to explain to you how cowait, coroutine works, generators, and some implementation details. Maybe we'll have time to discuss future a little bit. So let's start. Asynchronous programming is a very tough field, so we need a good metaphor. And this is the first talk in English at a conference ever for me. So yeah, I asked Jens, the organizer, and they don't refund. They don't give you money back. And okay, for synchronous variant, we will use the metaphor of making a tea. What we need to do is to boil water, obviously, to make a tea, to wait a bit until it is ready, and then we can drink it. And everything happens synchronously. An asynchronous variant will be, we want to start an operation that boils water asynchronously. We need to wait then for like 5 minutes, doing something useful, for example, read a book. Then we make a tea, also asynchronously. Then we need to wait for the tea to be ready. Then we don't have to stare at it as it is going to be ready. We can do something useful again. So go get some jogging, for example, I don't know. And let's see how std future works. So we schedule a task. In this example, it is a lambda that boils water for us and makes tea for us. And we don't want to wait for it and stare at the kettle while it's boiling. So we schedule it with the std async function, like that. The green arrow shows that the task is scheduled, and then we do something useful. Again, we can watch an educational video. And then we want actually to get the key, and the call to get logs if the asynchronous task is not yet ready. Parallel to that, we launched our task with a launch async parameter, and it runs in parallel. And when it is ready, our call to get is unblocked, and we can get results from that. And then we can drink out. Okay? Oh, I forget to mention that if you don't get something, please ask questions. Raise your hand. Our volunteers will give a microphone to you, and you can ask questions. Please, don't hesitate. Okay, next is the package task. It works very similarly to that, but instead we just say what we want to do instead of actually scheduling a task. So we want to do exactly the same. We create a task object. We then obtain a future from that task, and then we can use something that executes our task. Something like an executor or a thread pool or whatnot. After that, when we actually schedule our task, we again can do something useful. It is not shown here. We then, when we want to get the result of the asynchronous task, we call the get function method. Our task is executed parallel to that, And when it is done, we get our result. The call unblocks, and we can continue the execution. Let's go a bit deeper and see what's under the hood. Package task basically is implemented in terms of promise types, and promise object. And let's see what happens here. We have a promise and a future that we get from promise, and they're connected with a shared state where all the synchronization primitives live, the eventual result lives, and we can get the result from the task using that shared state. So there are cute puppies in my on my slides. That is done so you can then say, like, go to the slide with a puppy, not like go to the 13th slide or 9th slide, because then you need to say, like, no, the previous one, no, the previous one. You can say, like, go to the slide with the puppy, or the previous slide, or the next one. So what we have here is like an idiom that shows how to asynchronously update value. What we have here is, wait a minute, sorry. So we want to update this value asynchronously, and we want to tie our asynchronous operation to the lifetime of the actual object of type widget. So we do that by having our value in a state that lives in the heap, and we manage that lifetime with shared mutex. And when we want to update our value, we capture weak pattern to the actual shared pattern in our lambda that actually executes and asynchronously executes. And when the result is ready, we can ask if the state is still alive. If it's still alive, we can update our value under the lock, and if it's not still alive, we can just like return and do nothing if the state is not alive at that point. Any questions so far? Okay, let's go. Next, I want to talk about Parallel Patterns library from Microsoft. I'm not... Okay.
I'm not sure if you're going to explain it later.
Okay, sure. Wait for microphone, please.
Okay, I thought I'm loud enough, but the question is simple. The question is simple. Can you point out main differences between package task and the future? And the async you explained before, because if I remember the examples correctly, they more or less accomplish the same thing.
Right. A future is a primitive that, like, it's a handle for future result of an execution of some task. A package task is a primitive that handles for you exception handling and whatnot. It packages your, like, function or lambda that you can then schedule for execution. It hides boilerplate for you. Then you can get a future from that task. Then you, like, throw that task to some execution unit, to some, like, thread pool and whatnot. And you get future. You then do what you usually do with the future. You can call wait, you can call get. And yeah, if there is an exception in the task that you scheduled, you will get an exception when you call get. Did I answer your question? Please elaborate further if you want. Okay, right. So this is, I'm not like just telling you what there is in this library. This is just an illustration for the concepts. What I want you to get is concepts. The concepts are universal. they apply like in this library, in other similar libraries for asynchronous programming, and this is just an illustration. But if you want to use it, you can use it within CPP REST SDK, also by Microsoft. They implemented a subset of Parallel Patterns library there, and it works in every imaginable platform. So let's see what we have. We have a task type that is fully analogous to future type, except you schedule your tasks as well with construction of an object of type task. It is analogous to calling std_async with launch async parameter. And if you don't want to specify template arguments, you can just call create task and it will do it for you. And analogous to promise is task completion event, which does the same job. You can say that, okay, I have an event, I want like a future from that, a task from that, and I can set that completion event to so it is ready, so my task becomes ready, and if you wait on the task, your call is unblocked and you get the result and can continue execution. Okay, task unwrapping. If we have a function that returns a future and we want to schedule its execution in another task in another function that also executes asynchronously, we now have to return a future of some return type. In this example, it's void. So this is unnecessarily complicated, and we can do better. And PPL implements a so-called task unwrapping. You don't have to return task of task of task, whatever. You just return task, and it magically works. So here we schedule our task. In the constructor, we pass our lambda that does the work for us. And in that lambda, we return the result of the asynchronous task that in turn returns a task. So now we scheduled our task. It went executing parallel to our main thread. We called wait, it blocked, and we wait until all the internal work is done in our asynchronous task. So when the outermost function returns, it returns the result of make async task, which is task, an object of type task, and it unwraps under the hood, and it's knowledge that we have to wait for another task that executes somewhere else asynchronously, transfers into the outermost object that is T, also of type task. So when the innermost function completes execution, it makes its task ready. This knowledge comes to the outermost object, outermost task, and we get our result, our call to method wait unblocks, and we can continue the execution. Okay. Other questions so far? Okay, don't hesitate to ask questions, please. Next concept is continuation. What we in fact want is some way of compositing our task. We want to say that, okay, I launch an asynchronous task, but when it finishes, I want something else to do after that task is finished. So this is accomplished using continuations in terms of the then method. Here we schedule our first task that boils some water and returns some message to the caller. Next, we schedule the next task. And the first task may not even start to execute. We're just scheduling our task. We compose the tasks. So now we call wait. We wait for execution of all the tasks that we composed. First, our first task is executed on some parallel thread, maybe. Then the scheduled second task is executed. And after that, it is finished and we can get our result. Our call to wait is unblocked. And we can get the result and continue execution. What about exceptions? How that work? Here we have chain continuations, chain tasks that are scheduled like one after another. And in the first task, we are so unfortunate that we throw an exception. What happens next? That exception is handled and it is transferred to the next continuation. It receives a task. So that knowledge that the previous task had an exception is transferred to the argument to the next task, next continuation, and we can get it from that task object if we ask for it. So that way we can handle exceptions that were thrown in the previous tasks, previous pieces of work. And here we are unfortunate not to handle that exception, and it's handled again by the runtime of that PPL library. And now, since our next continuation doesn't receive its argument as a task object, it cannot handle the exception, and so it is not called. And the knowledge that the exception happened transfers directly to the outermost task object, that is T. So we called the method wait. It blocked everything inside our scheduled functions, scheduled work executed. We had an exception, and now we can call our wait, and in fact it throws an exception because the knowledge that the exception happened transferred to this object. Okay. Cancellation, in my opinion, very important topic because we have next to nothing to do proper cancellation. We basically can only terminate the process or thread, which is not desired, because we want to finalize our resources, finalize our operations. And this primitive is relatively simple. We have a token source for cancellation tokens. We can obtain objects, cancellation tokens from that. And they are connected internally. And when we want to cancel, we call cancel on the source, and on the token object, cancellation token that we distribute to our task, we can check if task was requested to cancel. If it was, we can gracefully finish or cancel our operation. If it tells us that we can continue, we can do some useful work. So there is another great feature about that. We can register a callback that is called when it is requested to cancel. So we register our improvised stop boiling call that stops asynchronous boiling of the kettle, and then we start actual boiling process, asynchronous process. It does not return it doesn't. It is synchronous process, but we can cancel it asynchronously. It executes. It doesn't return anything until it is done. But since we registered call to stop, a cancellation mechanism, when the cancel is requested, it calls stop boiling, possibly on another thread, and the process cancels, stops, it returns, and we can continue execution of our task and gracefully finish execution of our task. Makes sense? Okay. Since I have a one node, I'm going to continue. There is a proposal to the standard that implements almost exactly the same primitives. It's called stop token by Nico Yusutis and his colleagues. And I think it's brilliant. You should use it when it is available in your compiler, in your environment. Next topic is composition of tasks. So if you have several tasks, several independent tasks, and you want to know when all of them are ready, you can call when all method that returns to you task object, result of which is the actual set of results of your asynchronous operation that you are scheduling for execution. The other primitive, it returns a vector of results of all the tasks you're going to schedule for execution. The next primitive, the other primitive, is when any. You can use it when you need results, when you schedule many tasks, but you need the first result that is ready. So as a result, it returns to you a pair that is the result of one of tasks that you scheduled and the number of that task that has finished first. Then, when you, for example, get the result from the first task, you can call when any again. Just remove that finished task, and you get again eventually the result of the next finished task and its number. So again, as I said, it returns the result of the finished task and its index, its number. Okay, I said that there are puppies in my slide, and it's a C puppy. We'll hide it for a bit. Here is another idiom, mind-bending idiom. We want to do like a do-while loop, but it's not really a loop. It's just a virtual loop of scheduling and execution. Let's see how it works. So we go into the function, we schedule our function that we want to execute in a kind of loop. Then we schedule the continuation, that is the body of this lambda, and then we just return the task object that we got from then call. What happens next? Our function is executed possibly on another thread, not possibly, definitely on another thread, because PPL uses in its runtime a thread pool for execution of asynchronous tasks. So it executes, it returns a Boolean value that says, do we want to execute it further one more time? If we want to execute it like at least one more time, we go back to our lambda that schedules further execution. Let's say we want to do that, then we call kind of recursively, but not really recursively, do while again. we schedule again the next execution of our function. Then it returns. Let's say we don't want to run it again. We again return to scheduled execution of our lambda, and we just return a result. That is, the result is like completed task. We completed our asynchronous loop. Make sense? Okay, please.
Thank you. So the moment when we stop, when we exit the loop depends on the need to continue parameter,
right.
But
it depends on what the function that we pass to the do while returns. So it returns something convertible to bool. We look what the previous execution returned, and if it says that we need to continue like our loop, we again schedule the next execution by calling do while, and it repeats.
Okay, thank you.
Makes sense? Okay, here's our C puppy again. Next idiom is cancellation of several requests. This situation happens when you want to schedule several requests, kind of requests, asynchronous tasks, and you want to cancel all of them, all the requested operations. In this situation, you want to have a cancellation token source that from which you get cancellation tokens. You distribute it to all scheduled operations, to all requests, and then when you call cancel all requests, you like propagate knowledge that you want to cancel all the requests, and then you assign a new value to the token source, so you can start the process over. So you schedule new requests, possibly multiple requests, that you can then cancel again all in one call. Make sense? Okay. Here's the next idiom. In fact, you want to change your continuation. You don't have to see every line of that code. I just want to illustrate that you want to like stack your asynchronous operations in calls then to then. In fact, you should look at it like that. Like you want to concentrate on what's inside calls to then, and you can kind of see your synchronous operations written down as synchronous operations. And yeah, it's a forest puppy. So I like to go to this site from time to time to see what goes into the next standard. And when I saw that coroutines made it to the next standard, I celebrated like that. Yeah, that line was like meant a lot to me. So let's see what coroutines offered for us. Again, we'll use some kind of task. PPL supports out of the box coroutines. So all the stuff, all the magic stuff that you need to call wait and call return on tasks, concurrency tasks. So here we have two asynchronous operations that return tasks. And without coroutines, it looks like this. You call then on the return type of the first operation. Inside of the second, you can call the second operation. It returns task, it unwraps, and then you can add next operation that maybe returns some message that something our T is done. It's ready. So this is without coroutines, and with coroutines it translates to this. Again, for comparison. This is without coroutines, this is with coroutines. Isn't it pretty? Okay, let's try to see another example, then we'll try to see what happens under the hood. Here's close to production code that does an HTTP request, then watches what came from the response, what code, if it fails, if it not fails, then it makes another request to get an avatar of the user, and so on. And this translates. So yeah, you should look at it like this. In fact, concentrate on what's actually happening, not all the boilerplate. And this translates to roughly this. This is not so pretty to compare, but I think in fact it's more understandable. You can more easily reason about that. So we'll return to that. Okay. Why do I need coroutines? Why do you need coroutines? Why do we need generators that are like a specific coroutine? Generators between the co-yield between returning results save its state. You don't have to worry about state between calls. So you can even run an infinite loop inside a generator, and in most cases it will be fine. But in this case, obviously, it will run forever. But you can fetch as much number of values as you want, and it will go so many times as you need, saving state for you, and so on. So is it really syntactic sugar? I think it's not, because coroutines in fact do a lot of useful work under the hood. Compiler transforms code for you, so you don't have to do it. So let's see what are coroutines. Coroutines are in fact like a sister to routines. They're kind of the same entities, but the main difference of that is you can suspend coroutines. You can call routines and coroutines. You can get a result from that when they return. But the main difference in that you can suspend coroutines in the middle of the in the middle of the body of coroutine. So in C++ we got stackless coroutine. We didn't get stackful coroutine for now. There are debates whether we should and how to make it. But for me personally, this is enough to make many problems go away, like particularly with asynchronous programming. So let's see a little bit deeper what are coroutines. Any function becomes a coroutine if it contains at least one of co-await, co-return, and co-yield. And you can tell if a function a coroutine outside of it, because it is not stated in the signature of the function if it is coroutine or if it's not. It's an implementation detail. So let's see what everything of this does. Co-await roughly translates to this. When you call co-await, we have a coroutine handle, so-called, in the coroutine frame. We'll get to that. So in this particular example, we co-await call translates to operator co-await, and we get an awaitable object of some type, some awaitable type. We can call three methods of that object await ready if the result of the operation is already available, and we don't have to suspend the coroutine. If the result is not available, we suspend the coroutine, passing coroutine handle to the await suspend function. Eventually, when the result is ready, we resume coroutine from outside, and await resume is called. So yeah, let's recap. Coroutine handle lives in the coroutine frame context. This await suspend in fact schedules continuation using coroutine handle, and await resume returns the resulting value from the co-wait construct that you can see here. So the result of the await resume is the result of the this syntactically sugar call or construct co-wait boiler water sink. Makes sense? This is hard stuff. This starts to be hard from here, and it goes downhill from that, from here. So what here happens behind the curtains? If we have all of that in one place, when you write something like this roughly translates to this. We have our coroutine. We have a promise type in our coroutine context that is used to communicate between coroutine and the outer world, so to say. The compiler generates code to have a return object that we return on the first suspension, and it is obtained by a call to get return object from a promise object. So we go inside this body. If you set a breakpoint, you can see that we're still in main thread. We have this stack. You can see some compiler generated stuff that is called. Next, we schedule our first function and immediately return from this call. So then our function asynchronously got executed, it returns, then we schedule our next call. If you set a breakpoint, you can see that it is in fact already on another thread, on the working thread of the thread pool, for example. We schedule the call to the next function. It is also async. We suspend our coroutine the second time. After the asynchronous operation is executed, we again resume the coroutine, and if everything goes right, we go to final suspend. And final suspend in this case does nothing. It doesn't suspend. It doesn't cause to suspend the coroutine, and we propagate our result to the returned object. Returned object is like a task std string. So we make, by doing all of this, our asynchronous operations executed, and the result of that is propagated to the returned task object. Make sense? Any questions? Okay. Yeah, we can put a breakpoint there, and we see the similar picture that this is executed on some thread pool, on worker thread, not on main thread. Core yield that is used in generators is just a syntactic. This is like literally a syntactic sugar for this construct that is co-wait yield value. With this mechanism, we can return from the generator coroutine values repetitively. So this is all good and fun, but what's wrong with our current primitives, namely std future? In fact, it is unnecessarily slow because it involves memory allocations, synchronizations, that is not useful in every circumstance. So in some circumstances you can live without synchronization, it will be okay. And overhead for scheduling tasks. Currently you can schedule only by calling std async and passing everything you want to be scheduled, and this is unnecessary overhead. We have a proposal to the standard again that will add lightweight task, but yeah, the committee said that task is too like they didn't want to give away that name easily, so they said that you should use a different name, for example, std lazy. Until then, you can use excellent library by Lewis Baker, CPP Cora. He's done all the heavy lifting for you, all the job. You just need to download it and use it. Let's see what exactly is wrong with how exactly it is wrong with future. This is our baseline. We don't use any execution on parallel thread. We just use deferred execution. This is asynchronously calling our stuff inside of lambdas, not on different threads, just like deferred, in a deferred manner. So this takes, let's say, 1x of speed. If you use concurrency task, it's much worse, because there is no facility to make deferred execution. It always offloads the execution to threads, and that involves heavy penalties, and we have significantly worse performance. But if we use lightweight task, it is roughly 3 times faster than the std future and its facilities, std async facilities, and something like that we'll get in future standards, definitely, because it is actually ridiculous that we have coroutine framework now and we have no out-of-the-box facilities to use it. But yeah, we can write our own, or we can use already libraries that are already there. For example, CPP Cora by Lewis Baker, that I recommend. Here the recap. So we, for raw calls, obviously we have nothing, no overhead, but that's not the point. We want our code. We want our code to be easily, to be easy reason about, and still execute asynchronously, not synchronously. So coroutines approach allows us to minimize overhead and still have asynchronous operations and good reasoning about the code. So I don't know, do we want to go through the actual implementation of lightweight tasks? Let's go quickly. So if you saw the talk about coroutines today, you can already know that we have to implement a promise type that will allow the framework to do some job for us, so we don't have to. We have to have a getReturn object method that returns object that will eventually be returned from the coroutine on first suspension. And eventually, if it doesn't suspend, if it runs to the end of the body, still this object will be returned as a result. We have initial suspend. It tells whether we need to suspend the coroutine immediately after start. This is useful for generators. If you don't want the generator to return next value immediately, you want it to always suspend from the start. Similarly, final suspend tells whether we need to suspend execution at the end of the coroutine. Here we actually return an awaitable type that tells whether our result is ready, does the suspension by adding continuation to our previous task, to our current task, actually, and resumes the continuation that we have. And we have await resume, which implementation is on the next slide. And yeah, we return the awaitable type that tells what to do when we run to the end of the coroutine. We have to implement the unhandled exception that is called when exception happens inside our coroutine. In this example, we have to have return void. Otherwise, if we return not void but some type, for example, as the string, we have to implement return result function. Yeah, that's basically it. So next we have our actual task. That we operate with. We have to have this type def, this using declaration, so the framework, the coroutine framework, knows what type to use as a promise type. Next we have our constructor, our destructor, that destroys the coroutine. We have cowait operator. This is one way to interoperate with the framework. It again returns an awaitable type. So here we again schedule our continuation. So if this coroutine suspends, we tell how to resume the coroutine when the result is ready. Eventually we return the awaitable type with this coroutine as a context. And yeah, that's basically it. This is hard stuff. I hope that I got something across to you. I encourage you to investigate it on your own further. Don't rush. Take time. And yeah, this is the end of my talk. Please raise your hand if you learned something today. Okay, nice. Thank you.
So, about the coroutines, because I think that's the hottest topic today. Do you think that the industry, the C++ industry, will adopt coroutines quickly in general, without having much support in the standard library? with the types, because writing them on your own is looks like a real pain point, and I actually tried it, and it is a pain point. So, yeah, what's your opinion on that?
I think it's complicated. I definitely would use coroutines when they are available, like officially available on the next versions of the compilers and environments. But yeah, you're right that this is maybe it's an oversight that we have a framework, but we have no facilities to use it out of the box. I have no satisfying answer for you. Sorry.
Okay, thanks.
But yeah, we have at least CPP Core library that you can use right away. You can use it right now. I think if you want to, you
do you remember which compilers actually support it? Because I think not all of them actually do.
Definitely MSVC and Clang support it now, recent versions. I'm not sure about GCC, but I think they support it too now in what's the recent version 9?
I can't remember.
This is in the standard, so eventually all of them will support it.
Okay.
Could you go back to the slide before the first C puppy, please?
Okay, excellent.
So my question might seem a little bit weird, but anyway. So imagine I have a problem. I don't see.
This is the slide with the C puppy. This is the previous one. The previous slide.
But when any? Yeah, exactly.
Okay.
Yeah. So imagine I have a big problem. I have 2 strategies, 2 algorithms for solving it, and I don't know which one is the best for the problem. So, and I only have 1 core. So, does it make sense to start both of them and then use weight any? Or are there issues with balancing, overhead, such things?
Okay, it sounds like a silly question, but it's not. First of all, if you want to start both algorithms simultaneously and see what algorithms returns first, you can do it, because even in 1 core, because the current implementation, the PPL implementation, it schedules the work on thread pool. So with threads you have suspension and resuming of the threads, not coroutines. So if the time sharing strategy is fair, that might work, yes. It will work better with 2 cores, but yeah.
I don't have the choice.
I
Okay,
think it kind of makes sense if this is concrete task you want to have that you have.
Thanks. Let's talk about cancellation and PPLX. Suppose you have implemented cancellation to open source and cancelled it, but you haven't implemented cancellation points in the task. Is it useful?
In fact, I implemented the cancellation token, a stop token.
Yes, here.
This is not in my implementation, but yeah, I think if you did not implement cancellation points, right?
Yes.
Does it make sense?
It will.
The obvious answer is it doesn't make sense, because you don't check if it's requested to be cancelled or not. But if you have some option to call like in this slide, to call a function that cancels your operation asynchronously. For example, you can close a socket, and your operation, for example, read or write to the socket, will cancel also. So if you have a synchronous write to the socket, and you close the socket on the other thread, it kind of makes sense to do that. Makes sense? If you have no option to cancel your operation, it doesn't make sense. If you have some way to cancel your operation, yes, it makes sense.
What I mean, I have cancelled the operation, but the task itself, or the chain of task in the chain, doesn't call is cancelled.
Okay, look, if
then
you
I
say
think
that...
it will take no effect.
Right. What you can do is you can take your chain of tasks, put a check between the tasks in your chain, and that will help a bit.
I check usually in the start of then continuation.
Come again, please.
I check usually at the start of every continuation, of every then.
That will work, yes. That makes sense. Okay, I think that's all. Thanks for coming.